Previously, I implemented input, but in a rudimentary way. Looking at this demo, it looks pretty simple and unimpressive, and it is, but that's not important. Tabbing between these panels, pressing the Enter key on each to highlight just that pane's text, poses a challenge when all you know is if a key is down, and that's what we're going to solve today. Today is all about implementing an actual featureful input system. It'll have input layers that each of the panels can push when they're active, and an input stack that remembers who had input when. Input layers will have key presses bound to InputActions, which is the game state defines and then gives to these panels when it creates them. It'll be much easier if I show you. The problem with input between multiple systems, or objects even, is that it can get very chaotic if the input isn't managed by anything. So I like to use an input stack system in most of my projects, DOS or not, with the simple idea: any screen, any object, or anything that wants input has an input layer. So for now, we'll start with the persistent system layer. The game will push this on to listen to things like escape for quitting. And then a hypothetical game layer. This one manages all of the gameplay input as opposed to input for the UI. So if we press keys, they're checked on the game layer first, and if that doesn't use them, the key presses will trickle down to the system layer. So let's say we press escape. The gameplay layer doesn't want anything to do with that, but the system layer takes its cue and opens a quit confirmation. The UI layer pops onto the stack now, waiting for the enter or escape to confirm quitting. But this layer is opaque. This means that any key that this layer doesn't consume does not trickle down to the ones beneath it. It consumes all the keyboard input. This allows a dialog like this one to prevent the game layer from accidentally getting key presses that we don't want it to. We've essentially paused the action. If the player hits escape, the UI layer pops itself off the stack and the gameplay can resume, and so does the input. And that's really it for the input layer and stack system. Input is pushed to the stack, and layers consume input, aka prevent it from falling through when they use the input or if they're opaque. With creating our input layer, there's a few additional data structures we'll need to create. Since it holds a hash map of actions, we'll need the hash map, but to create the hash map, we'll need a hash string to use for our hash keys in the hash map. Hash. The hash string is a no-frills, by-the-book implementation of the DJB2 hash string. I'm not a computer scientist, but a brief Google tells me that this one is one we've been using since 1991, created by Daniel J. Bernstein. How about that? For those unsure of what a hash string is, it's essentially calculating a unique numeric value from a given bit of text. The 5381 you see in calculate hash function is a prime used to reduce the amount of potential collisions, as in hashes that match multiple strings. This number was just found by trial and error, which was something I was very curious about. With the hash string created, we'll now create another no-frills by-the-book implementation, this time for a hash map. A hash map is essentially an array that associates a hash string with a bucket, and the bucket contains a list of entries for all the values that the user passed to store in the hash map. Note that there's generally a limit in the amount of buckets, 32 in our case, so it's using a modulo of the hash to generate the index. The only real caveat with our hash map is the deleter function. Since there's no template substitution failures, not an error, or SFINAE patterns, or template specialization, we can't know if the value passed to the template class is an object or a primitive, or if it's a pointer that needs to be deleted or destructing itself. So I have to manually pass a deleter function that will handle this if necessary. Additionally, a smaller caveat is that the getIndex functions, the function that calculates or retrieves a hash and converts it to a bucket index, we manually override here rather than try to use template specialization because, again, in 1993 we had no such thing such as template specialization. The next bit we have to put together is the pointer vector class and the ownPointer class. These are helpers that are clunky ways to take care of things modern C++ compilers have elegant ways to handle, but we do not. The purpose here is that our original vector class had no concept of allocating or freeing memory if it necessarily had to, for like moving things around or the remove. And since we don't have a shared pointer system, the ownPointer also lets us pass around a pointer like it's a unique pointer, freeing itself if an ownPointer is still holding it when the ownPointer falls out of scope. The vector pointer class is a carbon copy of the vector class with one small change. The data is an array of ownPointers rather than the data type itself. This really is only explicit in the accessors, but also in the grow function where it allocates new memory for growing. Now we have all the foundational stuff done, we can move on to the input binding and input actions. Input binds live on the input layer in this implementation, and it's how the system associates raw hardware input, aka key presses and mouse buttons, with actual in-game actions. The input layer uses our new hash map to store a hash map of unsigned integer keys with VG input action pointers. This is because the unsigned integer is storing the key code for what was pressed, combined with the action of press or release. This way, when we're creating an input layer, I can bind specific keys to specific actions. For example, I could bind escape to the action pressed to an input action that opens the pause menu. Input actions are a simple class that inherit from VG input action, but each subscription just makes their own descendant of that class, with the real meat of it being in the React function that works like the layer and other React functions. Return true if you consume the input, false otherwise. From there, any game system can store whatever they want in this class, do whatever they want with it, and the React function is basically the execution entry point for that action. The one thing that it does do is when it triggers the subscription, it will also pass what the pack key and what the action was, just in case those are useful for the user of the class. Finally, to put it all together, VG input, the core of the input system, pulls the input stack, traversing top-down until each packed action is either consumed or blocked, and then moving on to the next layer. Because the keyboard class makes use of the interrupts to read the keyboard, I'm actually going to be using a ring buffer here as a way to store the inputs in the devices class and read them in the input class. A ring buffer essentially is what it sounds like. You push and pop into it with filling it starting over from the head of the list. With that, the disable and enable functions become far more important in VG Keyboard's interrupt handler. Since interrupts could enter the program at any point during execution, these ensure that the keyboard and input system essentially don't fight over the input stack. With the input stack and all its components complete, the last thing to do is set up a simple test of the input. I've set up 3 different handlers here which highlight a different box depending on the key press. The main important bits to pay attention to here are the input subscriptions. In this example, we're inside a create panel setup that creates a panel, gives it a label, and then makes a subscription to the enter key and the tab key. You can see the VG input action. Here it's called InKey, and it's doing the bulk of its work in the React function. I actually made this one class able to be bound to either the enter key or the tab key, so it'll handle either key action type, reading the action function from the parent VG input action class. You'll see it just has a constructor and a React function, and that's all it needs. Now we see the example. Tab key is swapping which numbered box is selected, while enter is lighting up the text inside the box. This is really just demonstrating that despite all 3 panels being bound to the same keys, only the one on the top of the stack, the focused one, is responding to input. Whoa guys, if you've been following along since the earlier videos, you've been waiting a long time for this. And if you haven't, well then, I mean, it's still here, bully for you. I would have liked to get this out about 3 months ago, but things like life happened. I spent a significant amount of time also creating an animation program to help me with my little chalkboard animations, and that ended up only making 1 of those for this video. I wanted to do way more, or at least 1 more. I wanted to do the input actions, but I didn't want to delay the video any longer. Anyway, no promises on when the next one's coming, but another one is coming. We're crawling our way towards actually making a game real soon. I mean, soon is relative. A game called Meat. I'll let you stew on what that could possibly mean, but please like and subscribe if you like and subscribe to this video. Number goes up feels really motivational to me and many others of my generation. Alright, love you, bye.